Hi, my name is Scott Cheatham, and I am the teacher that created this lesson for you on an introduction to solving systems of equations. Solving systems of equations is an idea that comes up starting in Algebra 1, but then again more in depth in Algebra 2, and as you go further into trigonometry and calculus. But what we're going to look at today is where you first start to see it and how it gets used in Algebra 1. And so I hope this will be beneficial for you as you're doing this. Just so you're aware as you are going through this, the slides are kind of move as I'm talking, but if you need to pause and go backwards, or if I say to pause, you can do that in PowerPoint, and then when you hit play, it'll kind of pick right back up. So kind of take it as you need to as you're going through the speed. Just want to start by asking the question, what is a system of equations? That might be a term that you've heard before. And so I just want you to think what comes to mind when you hear that term, a system of equations. And so I just want to take a second, think about it, and see what you remember. If you've ever heard that term before, what you recall. And I'll just kind of start by generally saying that a system of equations really just means there's more than one equation. For the most part in Algebra 1, when you start learning how to solve equations, you're dealing with one equation and one variable. Systems of equations are ways that we can solve problems that have more than one equation and oftentimes more than one variable. And that's especially helpful as we look into ways that mathematics gets used in real life, in real life scenarios, in both business and in real world applications. Systems of equations where you're solving for two different variables and you've got a couple different equations or rules that you're trying to incorporate together. It's a way that algebra really gets used in the real world. And so as we're moving forward, there's going to be a couple different ways that you'll see this and be able to solve it. Some it's going to be more just kind of algebraic looking, meaning just a bunch of numbers and variables, and that's a good way to start learning it. And then as we evolve and how comfortable we feel with this, we're going to move to where we have word problems and talking about how we can go ahead and use solving systems of equations for word problems in those real world contexts. And I want to start by giving you an example. So this example is something where I'll go ahead and read it. For Halloween, your parents ask you to buy 25 pounds of candy from the store. Now you purchase that 25 pounds of candy for a cost of an average of $2.70 per pound. Now the mixture that you got was two candies, and one of them was Sour Patch Kids that costed $3 per pound, and the other was jelly beans, costing $1.50 per pound. How many pounds of each type of candy were bought? Now, what I'm going to ask you to do in just a minute is I'm going to ask you to pause this PowerPoint and give it your best shot of trying to figure it out. Now, you might know how to solve systems of equations. You might have seen it before or have an idea, and that's one way of doing it. You could do a type of guess and check or some other method. There's a number of different ways that you could try and solve this. But what I would like you to do is to go ahead and give it your best shot of trying to figure out how many pounds of Sour Patch Kids and how many pounds of jelly beans did you end up buying for this problem. So go ahead and pause the PowerPoint now. Now, I'm not whether you were able to solve that problem or not, that's fine. We're going to come back to it after I show you some ways of solving these, and I think it'll make a little bit more sense how we're going to approach the word problem. But I always like to start with showing you kind of a real world example before we kind of just jump into a bunch of numbers and variables here. But for solving systems of equations, this is a common way you'll see it. You'll often see the variables x and y, although it doesn't have to be that. And you'll often see it written like this. Okay, so solve these problems where we've given you two equations If you have two equations and two variables, that should be enough information to solve it. You just kind of have to know how to move things around and manipulate it. And so we're going to start by looking at number one. Now, the first method that we're going to look at is what's called substitution. And we're going to do exactly the way what that sounds is we're going to substitute. Now, I'll go ahead and start to say this as I start showing you some of the work for these. The ways that I'm going to show you are not the only ways that you can do it. There are other ways that you could do it. Namely, if we're substituting in for y, you also could substitute in for x. It just really depends on how the problem's set up. Oftentimes, as is the case with this first one, there's one variable that's going to be easier to use for substitution, but you could use the other one. It just means you're going to likely have some fractions, or it might be a little bit more messy. But all the math would work out the same way in the end as long as you did everything correctly. So for this first one, we have two equations that we're going to accept as true, and we're going to use them to solve for what value of x and what value of y could we plug into these equations and would make them accurate. So for the question one, we have y equals 3x minus 1 and 8x minus 2y equals 14. We want to know the ordered pair, the x and y values, that would work for both of these. And for the most part, it's just going to be one ordered pair that's going to work for them. Now, this is called substitution because what we're going to do is we're going to take one of the variables and we're going to want to get it to where it's just either x equals something or y equals something, and then we're going to substitute that into the other equation. And that's important. You can't substitute something into itself. We got to substitute it into the other equation. And so when you look at this first one here, we have y equals 3x minus 1. It's already set up that y equals this. And what we're going to do is we're going to substitute that into the second equation. Now, as you see here, I've kind of got a bunch of the work already kind of worked out. But if you kind of look along, you can see that I substituted y equals 3x minus 1 for the y in the second equation there. And then from there, now it's just doing a little bit of algebra and solving for that multi-step equation there. But the benefit now is that we are down to one equation and one variable. And that's what we need in order to be able to solve this. So the benefit here is if you go ahead and do the algebra there, you've gotten yourself down to where it's just one equation using x. And you can go ahead and solve that and you get x equals 8. Now from here, we then need to go ahead and substitute that 8 back into the other equation. Really at this point you can substitute the 8 into either equation and it will give you the same y value. I chose to substitute it into the one that was a little bit easier. 3 times x minus 1, 3 times 8, minus 1, that's should be it's 3 times 8 minus 1 there, it's 23, and we get our answer. Now, the second problem here is not as nicely formatted as the first. The second one here, we don't have x equals a number or y equals a number, and so we've got to do a little bit of manipulating in order to get there. And there are literally 4 different ways we could do this. We could isolate the 2x or the 3y and try and get them down to x or y. Or in the second equation, we cannot try and isolate x or the minus 5y and try and get them down to an x or y. Now, while I did say there's 4 different ones we can use, the easiest one is going to be, I believe, that x in the second equation. Because it's already down to 1x, all we got to do is move that minus 5y over to the other side, and then we can do our substituting. And when you look at this, you'll see I solved for x equals 5y plus 9. And then I went ahead and substituted in. Again, we have to substitute into the other equation. So the 2x plus 3y equals 5. Substituted in x there. Substituted in that 5y plus 9. And then it's just doing the algebra and going from there. When you go through that, you get y equals negative 1. Again, I could have substituted into either one of the equations and ended up getting the correct answer there. You'll notice I wrote my final answers as an ordered pair. It's 4, negative 1. If you wanted to leave it x equals 4 and y equals negative 1, that would be fine also. But that's basically how substitution works, is if you can get it to where it's an easy way to solve for x or an easy way to solve for y, that's often an easy way to do it. Now, unfortunately, it's not always an easy, nice, clean way of doing that. Sometimes if you were going to try and go to substitution, you're going to get messy fractions. And so there is another way of doing it that we're going to look at next. The second way that we can solve for these systems of equations is by using linear combinations. Another way that this also gets referred to is elimination. That means the same idea. And basically, what this means is that rather than doing substituting, we're going to kind of use a little bit of algebra to add together these equations. And depending on how we have it set up, oftentimes we can add together these equations and end up canceling out one of the variables. And then that gets us to a process where we have just one equation and one variable, and we can solve and move from there. Now, if we look at number 3 here, we'll see we got x plus y equals 20 and x minus y equals 10. Now, in algebra, whatever we do to one side, we can do to the other. So in algebra, we can add 5 to one side as long as we add an equivalent 5 to the other. Well, here we're adding two equal things. They just happen to look a little bit different. And what I mean by that is we could add x minus y on the left, and we could add 10 on the right, and we have added, in effect, the equivalent same value. And so that's what we're going to do here. Let me show you what that looks like. So I've got x plus y equals 20 and x minus y equals 10. Now, when I add them, what I'm going to end up having is I'm going to have, and let me show you, 2x. And while it doesn't show it in the way I have this work, we basically have plus 1y added to negative 1y, which would cancel out or give us 0y. That's the goal for these linear combinations or eliminations, is we want to add them together to where we're eliminating one of the variables. Here we have eliminated the y's. And so you get 2x equals 30, and then from there it's just some working through some basic algebra to solve for x. We can substitute from there into either one of the equations that we want, whichever one looks easier to us. I've substituted into the one with the addition, and then solve from there. And again, we get x equals 15 and y equals 5. So this was probably a little bit easier than if I had isolated one of them and then substituted in, and then I think the linear combinations, if it's set up a little bit easy, if it's set up a certain way, it can be easier. It really just kind of depends on what your preference is. That's going to be a skill as you're doing these, where one way might be easier than the other. Both will work. It just depends on how messy everything's going to be. Now, when we look at this second equation over here, you'll notice that there isn't as nice and clean of a way as there was in problem 3 to cancel out the problems. We can't if we add 2x plus 3x, that's 5. If we add 3y plus 4y, that's 7y. So we don't have a nice, neat way of doing that. So what we're going to have to do is we're going to have to manipulate the equation some. Now, what I mean by that is, again, in going back to our principles from algebra, whatever we do to one side, we can do as long as we do it to the other. So I can multiply through these numbers on any side as long as I do it to the other side. Sometimes you can do this by just multiplying one of the equations to change the numbers to something that's going to cancel out nice and neatly. Other times, like this one, you actually have to do it to both equations. So let me show you what that means. So and then you go ahead and you substitute in to solve for that, and you end up getting 1 for y for an answer of 1 and 1. Now, let's go back to that example that had a word problem. And so the thing with the word problems is that it's not written out already in the two equations. We have to actually be able to think of what are the two equations are going to be. And honestly, that can be some of the hardest part for solving these. As you do it, you'll get more and more comfortable with when it's easiest to use substitution, when it's easiest to use linear combinations. The hard part is whenever you have a word problem, you have to decide, okay, which way am I going to go to solve and figure out what the original equations are. But I want to kind of help you with some of the steps for that. So again, you bought some candy. We ended up with an average of $2.70 per pound for the 25 pounds of candy you bought. They give you the price of the Sour Patch Kids and the price of the jelly beans. And then this is important. We got to circle back. What is the problem asking? Okay, how many pounds of each type of candy were bought? Well, that right there is what we're going to use for our variables. What are the pounds of Sour Patch Kids and the pounds of jelly beans? And I'm using X and Y here. You could use S for Sour Patch Kids and J for jelly beans if you want. That's fine. I'm just going to kind of keep it with with X and Y, which is what we've seen. And so once we define the variables, then we need to kind of look back at the problem and say, okay, what information are we given that I can use to pull out the equations? And so if you need to go backwards, by all means, you can click backwards and see. But I'm going to kind of talk through, okay, well, what information are we given? And how can we use those to come up with equations? So I want you to actually take a second and pause if you would like to, and see if you can go backwards, see if you can see what do you think the two equations would be that we would use in order to solve these. So go ahead and think about that and go backwards if you need to. Say, what do you think the two equations are? So the first equation that I have here is x plus y equals 25. And we're told that in the problem that you were asked to buy 25 pounds of candy. The two types of candy you bought were Sour Patch Kids and jelly beans. So x plus y, those two amounts, are going to equal 25. And so that one is pretty straightforward. And that's going to be our first equation. The second equation is a little more to it, but this goes to the cost per pound. We were told that the Sour Patch Kids cost $3 per pound, the jelly beans cost $1.50 per pound. And then, so if you were to multiply those by the pounds we bought, then that's going to be how much you paid. And we were told that it did an average of $2.70 per pound for those 25 pounds. So the trick here is that 2.7 times 25, it'd be really easy to forget the 25 or to forget the 2.7 or something like that. You really have to take all the information that we're given to be able to create this equation here. But those are the two equations. They are written in what we call standard form, where the x plus y is on the left and equals a value on the right. We might want to clean it up a little bit. And really from here, it's up to you to decide which way would you want to do. Would you want to do a substitution method, or would you want to do a linear combination method? It's really up to you to decide. What I want you to do is, now that I've given you the two equations, they may or may not have matched what you got when you were thinking of them. I want you to pause the presentation. I want you to try and solve these using either substitution or the linear combination method, whichever way you think is going to be the best for you. And then once you get through it and solve it, hit play again, and I'll show you what I did. All right, so the way that I solved this was using substitution. And really, I think that probably was the easiest because you've got x plus y equals 25. I already had the constants in front of both of those variables were 1. So it's really easy to isolate those and then substitute into the other one. You could have done linear combinations where I might have multiplied the top equation by -3. But again, I'd rather just kind of do the substitution and kind of go from there. And after you substitute in, really it's just kind of working through the algebra. You have y equals 5 is what you end up getting, 5 pounds of the jelly beans. And when I substitute in, I get x equals 20 for that. Now, one thing that I will say that is very easy for people to forget is that they don't necessarily answer the question. In a word problem, you need to say whatever units or whatever it's asking. And so in this case, it asks a little bit more specific for you to use the information and verbiage from the word problem. So we want to make sure we answer it. So to answer the question, even though X was pounds of Sour Patch Kids, we had 20 pounds of Sour Patch Kids and 5 pounds of jelly beans, and that is our answer to the question. All right, now what I have here is I have 3 problems that I would like you to do as independent practice. And what I mean by that is I want you to attempt them on your own. If you need to go back and look at how we did some, you can. I don't want you to go forward yet because I don't want you to see how I do them. I want you to attempt these 3 problems on your own, and then I'm going to kind of walk through how I would do each one of them afterwards. But what I want you to do is you can go ahead and you can leave this up after you pause it and go ahead and give these 3 a try. And like I said, there are often ways that I think are maybe easier in terms of deciding am I going to do substitution or linear combinations. But that's not to say that they won't both work. And you can certainly, when you're doing these, I would, if you get a fraction, that's okay. I would leave the fraction in there as an improper fraction. And that's oftentimes going to be fine and going to be correct. But so go ahead and I'll let you give these a try, and then we'll come back together and see how you did. All right, so before we go over the answers, I want to just give you the answers just as they are without the work. So look at these. If you did not get these answers, I want you to go back and see if you can figure out what happened. I oftentimes like to give people the final answers before we go over the work because sometimes you can go back and that can help you catch something without me having to point it out for you. So again, I wanted to give you the answers here. Let me know. Or actually not let me know, but we'll come back together and look at the work for this afterwards. But here are the answers, and if you didn't get them, go back and check and see if you can figure out what you did. All right, for the first one here, I chose to do a linear combination method. It didn't look like one where it would be easy to isolate it for substitution without getting into some fractions. And so for this one, I ended up having to multiply the top equation by 2, the bottom equation by 3. And when we ended up doing that, we ended up getting 6x and negative 6x, which worked out really nicely for us as we're going through and doing our eliminations. When I add both sides, I end up getting 0x, which is going to cancel. I had plus 10y and minus 9y, which when we combine those, we get positive 1y and equals 12. And from there, you get the 12, and I can substitute into either equation, and you end up getting negative 18. Now for this one little thing that's a little bit different in this one is that it was not written in what we call standard form, meaning it did not have the x plus y on the left equals a number on the right. You had to do some manipulating in order to get it. Now, it was already really nice and neatly in a substitution method, and so I think substitution, you could have just gone straight from that first one and substituted in the y equals 3x plus 5 into the next one. I didn't necessarily do that one. I wanted to go ahead and show you how you could rewrite it, but you could have right here gone and done substitution, and it would have worked out great. I rewrote it just in standard form, and the nice thing about doing that is it was already in a very conducive way of doing linear combinations and eliminating. And when you add the two, the y's were going to cancel nicely. And when you do that, you get 7x equals 0. Plug back in, you get y equals 5. And I think actually that if you had substituted the y equals 3x plus 5 to start, that probably was just as easy. But I wanted to show you the linear combination way as well. And for the word problem here, we had James is 8 years older than Pedro, and in 5 years he'll be twice as old as Pedro. How old are the boys now? Now, for this one, I went ahead, rather than using X and Y, I used J and P, just because we have people's names. You could have used X and Y or really any variables you wanted, but I chose to use the name, the letters from their names. Now, we've got to decide, okay, what are our two equations here? And so I will say that the wording here you really have to be careful with, because when you think you might want to say, okay, one of the variables plus 8, really you might want to say minus 8. It really kind of gets tricky, and you kind of almost, it's helpful to think of examples. Okay, so if I'm 10 and someone's 8 years older, they're 18, who would I be adding or subtracting 8 from to get my age? Or so you kind of have to be careful with those in how you're thinking about them. So I chose to do P plus 8 equals J. James, his age equals Pedro's plus 8. Now, the other way you could have done it, you could have reversed it and you could have said J minus 8 equals P. If you're taking Pedro's age, because he's 8 years older, subtracting 8 and getting J. And so, depending on how you want to set it up, there are multiple ways you could have done this. Now, with this one, I said in 5 years he'll be twice as old as Pedro. So in 5 years, James will be twice as old as Pedro. This one, you have to be careful where you're doing the twice. You have to actually do it with, if you're going to multiply by 2, you do that over to Pedro's side. If I wanted to do it over on James's side, I would have to actually multiply by half. So I could have done it that way. I could have done half times this. But notice I also had to add 5 to both variables to kind of get to where we were going, because it said in 5 years he'll be twice as old as Pedro. So this one a little bit more tricky in how you had to set up the equations, but I hope when you look at that it makes sense. Now from here I went ahead and moved things around to get it in standard form. I worked on some of the algebra there. You're gonna, for the first one, it wasn't too messy moving the minus j and the minus 8 to each other side. For the second equation, you had to do some distributing and then kind of moving things around. But here we get to one where it's kind of up to you if you want to do substitution or linear combination. Either way is going to require a couple steps, so I don't know that there's necessarily one way that's going to be overly easy compared to the other. It just kind of depends on your preference. I chose to multiply the second equation by -1. Which the benefit of that is that it got us to a very nice, neat linear combination that we could cancel the j's. When you do that, you end up with negative p equals -3. And by solving that, you get p equals 3. And you can substitute back in and get j equals 11. Now again, I want to make sure that I answer the question. So rather than just saying p equals 3 and j equals 11, I want to answer it. James would be 11 years old. Pedro is 3 years old, and both of those work for the parameters that we were given. I hope that some of these worked out examples and hearing me talk through them were helpful to you. As I said, as you do more of these, it'll become a little bit more intuitive to you, I think, whether you use substitution or linear combinations. Again, both will work in all circumstances, just sometimes they end up getting more messy with fractions, but again, both will work. These are two of the more algebraic ways of solving them. There are a couple other ways that are future lessons that you could look at, specifically solving them by graphing. That's the other way that's probably the most popular with these two in solving systems of equations. But as some extended practice for you, you may or may not have access to IXL if you're still working with our Richmond Hospital Education Program. At this time, we do have IXL subscriptions, and a number of schools use that. So some extended practice that you could do would be on there. Now, they use the term elimination rather than linear combinations, but that's something where it's the same idea and the same process. So I hope this lesson has been helpful for you. I wish you well as you're solving these systems equations and moving forward throughout your math class. Thank you.